All right, in 2.7, we're going to put together everything that we can about optimization. So take the stuff that we know about concave up, concave down. What we're really looking for usually are those top of the hill, bottom of a valley point. And think about the things that those points have in common. The first derivative, or the slope at those points, is always zero, because right, you're going steep uphill and then you hit a flat spot. And so the tangent line there is always horizontal. And then how do we tell the difference between one that's the top of the hill and the bottom of the valley? Well, this one is concave down, meaning that the second derivative is negative, and this one is concave up, meaning that the second derivative is positive. You can also do test points on the derivative, but it's usually, unless it's a complicated derivative, faster to do this. And so in some way, all the homework questions are going to find ways to ask us different things about these. And we'll just have to keep straight what function we're looking at. Okay, so one of the first ones, for example, gives us a graph of a line. And then they ask, they tell us the above graph is the derivative. So something to keep in mind, this isn't the original. This is just a tribute, or it's a graph that tells us the slope of the other one. So picture, we don't know what the other graph looks like, but I do know some important things about the original graph. I know that right here, if the derivative is giving me 0 at 2, that tells me that the slope of the original function is 0 at x equals 2. And so their question here is, how many critical points does the original function have? Well, the top of the valley, bottom of the hill, or bottom of the valley, top of the hill spots only happen when you have a slope equal to 0. Looks like this derivative only has one place where it equals 0, so it looks like there's only one place, one critical point on the original function. So we don't have to go too in depth about what the original function looks like. Like I know things like, see how it's a negative slope down here and a positive slope, so it's decreasing and then it's increasing. So maybe it does something like this, has a critical point right here. It's decreasing and then it's increasing. That could be the derivative of that one. All right, the next one, they give us the actual function, and they tell us, even if they didn't, we could come up with this on our own, but they tell us that the function has two critical points. But even if they didn't, if they just said, hey, where are the critical points? Well, first thing we need to do for critical points, those top of the hill, bottom of the valley, the only thing that we know about where they are is they're places where the derivative equals 0. So first, I'd probably like to take the first derivative of this function. So derivative of 2x to the third is 6x squared. Negative 42x squared is negative 84x. And then 270x to the first is just 270. And the derivative of a constant is 0. So here's our derivative. Then let's check, because if this factors, it'll be faster. If it doesn't, we can use quadratic formula. And I don't know off the top of my head, but we can really quickly in our calculator see how it has a front number of 6. If I could divide everything here by 6, it would make it easier to set this equal to 0. And it appears that we can. So if I divide everything by 6, I get 1x squared minus 84 divided by 6 is 14x, and 270 divided by 6 is 45. So even if this does factor, this would be easier to do from here probably. All right, so can I think of some factors that multiply to 45 and add to 14, or negative 14? Maybe negative 5 and negative 9. So x equals 5 and 9 will make this whole thing 0. So picture what we did from the beginning is we set the derivative equal to 0. So we're saying these are the points where the derivative is equal to 0, aka these are our critical points. All right, then we get a function where they ask us a whole bunch of stuff all about one function. All right, so first thing is we want the first derivative. At least this is the polynomial, so it's got separate terms. We don't need to do product rule or quotient rule. So it's a little bit easier of a derivative to take. So 24x squared minus 48x minus 72. And then they ask us about the second derivative. I'll just keep these color coded so that later if we have to do something with them, we can keep them straight. So we just do the derivative again. So 24x squared is 48x minus 48x is minus 48, and derivative of a constant 0. So now we have the first and second derivative. So now they could ask us to do almost anything with those. First thing they ask for is what happens if I plug a value into the second derivative. So if I put 3 in here, I get 48 times 3 minus another 48, so the same as 48 times 2, 96. Then they ask, based on the sign and in this number, does it mean that the graph is concave up or concave down? So we can just put up or down in our. So notice what we care about for concave up or down is whether or not this is positive. Since this is positive 96, what we're saying is that our original graph is concave up at x equals 3. All right, then they also say if the first derivative, and we could check this, but I think we'll take the question's word for it. The first derivative at 3 equals 0, so that means it's one of our critical points. So it could be the bottom of a valley or it could be a top of a hill point. They're asking which one is it? Is it a minimum or maximum? Well, picture, since we know it's concave up at this point, it looks like this, which automatically means it's got to be a minimum point. So we know it's a critical point. We know it's a place where the slope is 0. But then to decide whether or not it's a top of a hill, bottom of a valley, since it's concave up, we know it must be the bottom of a valley. So x equals 3 is a minimum, or it's where the minimum occurs at. If you want to know what the actual minimum y value is, you have to put it back into here. But they don't ask that in that particular homework question. So that's also called the second derivative test. It's just using the concave up, concave down to decide whether something's a maximum or a minimum, because it can only be, one or the other. All right, then we get another question. This is number 4 on mine. Sometimes they change the order, so it may or may not be number 4 on yours. And they give us a little window. I would definitely graph these. It's nice to be able to see them. Maybe I'll draw a little rudimentary graph on it real quick if I get a chance. But they ask for the absolute maximum and the absolute minimum. All right, up to this point, we've been doing what's called local minimum and maximums, meaning maybe this graph goes down to negative infinity and up to infinity, but just in this area, the top of a hill is the highest point right around here. It's not the highest point on the whole thing. Same thing with the bottom of a valley. This is the low point in its neighborhood. It's not the lowest point this thing gets to. So if they put the word absolute on it, what they mean is what's the absolute highest and lowest point on this? So what's interesting about these is that this is why they give you this interval. If this thing is starting at -4 and going to 1, so we'll say something like this. Maybe -4 is the highest point. It doesn't mean that there's not maybe another high point in there. And maybe 1 is the lowest point. Or maybe -4 is the high point. There's another low point, and it goes like this. So that one's the absolute minimum. It depends how it looks, right? And so to do this, we're going to find all the top of the hill, bottom of the valley. We're going to find all the places our first derivative equals 0, if there are any. And then also we're going to try the endpoints. So we're looking for which ones are the absolute highest and lowest is the difference. So the big thing is just don't forget about the endpoints. We're going to look for critical points, but we also have to test those endpoints out. All right, so let's see. The first derivative of this function, first derivative of 1 is 0, it's a constant, and then negative 6x squared is negative 12x. So if I set that equal to 0, it looks like it at x equals 0, we have a critical point. It appears to be the only one also, right? We only got one place with a slope of 0. All right, so now we have to decide which points are highest and lowest. So we essentially have 3 of them here to try. We have negative 4 because it's an endpoint, we have 1 because it's an endpoint, and we have 0 because it's a critical point. So we'll plug these all into the original function. So if I put negative 4 into this, I get 1 minus 6 times 4 squared is 16. So a pretty big number here. And if I put 0 in, I get 1 minus 0, so 1. And if I put 1 in, I get 1 minus 6, so negative 5. And this one is negative 95. All right, so they wanted absolute maximum and absolute minimum. So it looks like at x equals negative 4, there's an absolute minimum. That's certainly the smallest number we got out of this, right? There's an absolute minimum of negative 95, meaning this is where it's at and this is what the output is at that point. And then we have an absolute maximum the highest point in this whole thing is 0, 1. So at x equals 1, there's an absolute maximum of 1. So this is the highest output out of negative 95, negative 5, and 1.